Yes, good morning. Am I audible?
Good morning.
Yeah. Okay. So, yesterday we understood the lab program on the which one? Doubly linked list. Okay, the 8th program. And after that, uh, let me check the syllabus. Yeah. Uh, yeah. In module 3, this definition, representation of linked list in memory, memory allocation, garbage collection is nothing but freeing, linked list operations, traversing, searching, insertion, and deletion. Then doubly linked list you understood, circular linked list you understood, and header linked list also you understood, because the doubly linked list I explained with the header node itself. And then linked stack and queues. Okay. Applications of linked list, polynomials, sparse matrix representation. Both I have shown you already. The polynomials, how to do the polynomial addition. I hope you people remember. Hello.
Yes.
Yeah. So polynomials also I have done, and sparse matrix representation also I have shown you, and everything is there in my PPT. You can just refer that. And still there is one lab program which has to be given from the module 3, that is on the polynomials. Okay. We'll take up that later. Okay, I think there is nothing left here in module 3 to cover. Almost everything is covered, okay, including this polynomial and the sparse matrix representation using the linked list. So the next module is module 4, which is completely based on the nonlinear data structure. So what you understood till here was a linear data structure, so where the nodes are represented sequentially one after the other. So now we go for discussing a completely different data structure, that is trees, which is a non-linear data structure, because here the nodes are not represented sequentially. They are represented in the form of the trees. Okay. And then so many interesting things are there in this nonlinear data structure. So, and more important also. So here you understood how to traverse a linear data structure, how to search in the linear data structure, how to insert to a linear data structure at different positions, and how to delete from the linear data structure at different position. All these things you understood, and the same thing can also be done on the nonlinear data structure. But see, traversing the linear data structure is quite easy. But how do we traverse the nonlinear data, such as the nodes which are represented in the form of a tree? So there are different traversal approaches also here. So T traversal approaches, something like in order traversal, post order traversal, and pre order traversal. So these are the three approaches using which you can go for the traversing the tree in order to reach all the nodes of the trees. Okay. And similarly you can also go for performing the insert operation, delete operation, okay, and searching operation even on the nonlinear data structure such as trees. Okay, so the module 4 is completely on the trees, and a few applications of it also we discuss. Evaluation of the expression. Okay, so as we discuss the applications of stacks and applications of queues and applications of linked list and all these things, similarly we also understand the applications of the nonlinear data structure trees for evaluating the given expressions. Okay, so that is the module 4 completely. So, and here also I think 1 or 2 lab programs are there. Totally 12 lab programs we have. So from this if I give the program on the polynomials, 9 programs will be completed, and we have 3 more remaining. So I think 2 programs from the so 1 program from here, the nonlinear data structure trees, and I think you have 2 programs from the module 5. Okay, that is sorting and searching technique. On this there is 1 program, and I think 1 more lab program, I'm not sure, it is on this file and other files. Yeah, I remember. So the last lab program is on the files. Okay, so now we'll start with the trees, okay, for today's class, and the lab program on the polynomials we'll discuss it in the next week. Okay. So is my screen visible?
Yes, sir.
Okay. Is the brightness okay? Is it visible? It's visible, right? Clearly?
Yes, sir.
Okay, thank you. Okay, now trees, which is a nonlinear data structure. So this is what we are going to discuss. Okay, I've already told you briefly what is a tree. How does a tree look like? So a tree is something looks like this. Okay, see, it has a root node. Okay, and this root node has 2 child nodes. So this honey bear is 1 child node, and this is brandy is another child node. Okay, and this again has 2 child nodes. So this also has 2 child nodes, and this node has got 2 more child nodes. Okay, now the nodes which are at the bottom of the tree, we call them as the leaf nodes. So these are all the leaf nodes, because they don't have any the children node or the child node. Okay, so hence we call them as the leaf node, and this is the root node, and all the nodes which are between the root node and the leaf node, we call them as intermediate nodes. Okay, intermediate nodes. Now we are going to discuss the data structure trees, and we are going to represent the node exactly like this. Okay, now so again, say for example I want to represent a node in a tree. Now I got to create a node, so allocate the memory dynamically by using the malloc function, and then here also in trees a node should have the info field and 2 links again. Okay, 2 next field or the 2 link fields. So here, so this link field, the left link here will hold the address of the right subtree. Okay, and the right link here of this node is going to hold the address of the right subtree. Okay, so OP people are following. So now for this root node, this is the left subtree, and for this node, this is the right subtree. Okay, And if I take this as the node, for this node, so the left link will be holding the address of the left subtree, and the right link of this particular node will be holding the address of the right subtree. So hope you people are following.
Yes, sir.
Okay.
Yes, sir.
Now this is how you're going to represent the tree. Okay, and whenever I say a tree, so the number of nodes in the tree, depends on how many levels the tree has. So now this tree, what you're seeing here, as 1, 2, 3, 4 levels. It's a tree with 4 levels, and it is a completely balanced binary tree. Now how do I say it's a completely balanced binary tree? Because every node, see this has 2 child nodes, and if I take this again 2 child nodes, and if I take this again 2 child nodes, it's a completely balanced binary tree. Say for example, say if I delete these 2, please mute. Say for example, I'm deleting these 2 nodes here. So these 2 leaf nodes, assume I'm deleting this, then yeah, please mute. (154), please mute. USN 154. Okay, thank you. Okay, say if I delete these 2 nodes, so then it's not a completely balanced binary tree. So still 154 you have unmuted. So USN 154. Mute your microphone. USN 154. Okay. See, if I delete these 2 nodes, okay, then it will not be a completely balanced binary tree. Okay. So we have another tree, binary trees, just the simple binary tree and completely balanced binary tree. Now what you're seeing here is a completely balanced binary tree. Okay, next. Okay, definition of tree. So tree is a finite set of 1 or more nodes. So as it was shown in the previous slide, so a tree contains 1 or more nodes, but with a condition. What are those conditions? There is a specially designated node called as the root node. So one node should be there which is acting as a root node, the special node, and the remaining nodes are partitioned into n greater than 0, okay, n greater than or equal to 0, sorry, disjoint sets T1 to Tn, where each of these sets is a tree. Okay, so why we are saying this is, so I have a root node. Now this I told, for this node, so this is what, again a tree itself. Now what tree it is, I call it as a left subtree of this node, and if I look into this portion, this is again a tree itself, okay, which is a right subtree for this particular node. And again if I take this portion, this is again a tree which is a left subtree for this particular node. Okay, this, the remaining nodes are partitioned into n greater than or equal to 0 disjoint sets of trees. Disjoint set trees something like T1 to Tn. Okay, the other nodes are again partitioned into the trees again, but these trees, they will be either the left subtree or the right subtree for some other node, and we call T1 to Tn the subtrees of the root. copy people have followed. So this T1 to Tn, so what are they? They're all the subtrees of the root node. Sometimes some trees will be the left subtree for the root node, and some trees will be the right subtree for the root node. And similarly, as you descend from the root node to the level lower, so again you can take a node, and that node itself has what the left subtrees and the right subtrees. Next, level and depth. Okay, so we have, I already mentioned that a node will have, a tree will have the number of levels. Okay, now what you are seeing is not a completely balanced binary tree, because see this node E has 2 child nodes, but F doesn't have any child nodes, and G also, but H has 1 child node. Okay, so this is tree, no doubt, but not a completely balanced binary tree. Okay, and how many levels are there in this tree? So this has got 4 levels. Okay, so this has got 4 levels, and okay, so node 13. So if you count here, there are 13 nodes: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then degree of a node. See, every node has the degree. I hope all of you know this. Okay, node degree. Okay, so again, this node degree can be divided into 2 types. One is the in degree and out degree. So since the direction is not important for us here, so we are just calling it as the degree of the node. Now if I take the root node, its degree is 1. Okay, and if I take any intermediate node, so this intermediate node, if I am taking, so this node degree is how much? This as 3. So if it is a completely balanced tree, something like this, the root node will have the node degree 1, and the leaf nodes will have the node degree 1 again, but all intermediate nodes, they have the node degree 3. So this has the node degree 2. Okay, because why I am saying it has node degree, see, this is one line which I've connected to both. So, but strictly speaking, there has to be the 2 lines. That means the left link of this node will be connecting to this, and the right link of this node will be connecting to this. Okay, so that means the node degree for this root node is 2, and the node degree for this node is how many? 3. This is 1, this is 2, and this is 3. All intermediate nodes will get the node degree as 3. And what about the leaf node? So the node degree for the leaf node is only 1. Okay, only 1. Now similarly here, so node degree for this is how much? 3, because it has 3 child nodes, and node degree for this is 3, including this, and this, it is 3, and for this it is 2, and for this it is again 1, 2, 3. Oh, yeah. So 1, 2, 3, 4. Node degree for this is 4, and this is again 3, and this is 1, and this is 1, 1. Like this, every node has something called as degree, node degree. And then, so leaf node or also the terminal nodes. So this is the leaf node here, this is the leaf node, and F is also a leaf node, G is a leaf node, and H is not a leaf node, M is the leaf node. The nodes which doesn't have the further child or the children node is called as a leaf node. And a non-terminal node is this, all the nodes which come in between the root and the leaf node, we call them as the non-terminal nodes. And the parent. Okay, so say this is the parent for all this entire things, and if I take B is the parent of what? This particular nodes, and C is the parent of this. Okay, and if I take B as the parent of E and F, and what about A? A is the grandparent of E and F, something like this. So, and then siblings are also there. Okay, and then degree of the tree, ancestor, level of the node, height of the tree. Okay, so this is a tree with 4 levels. Now few important terminologies. The degree of a node is the number of subtrees of the node. Okay, so this is what I mentioned in the previous slide also. Okay, so degree of a node is the number of subtrees the node has. So degree of A is 3. Okay, so if you look into this, okay, so degree of A is 3 because it has 3 subtrees. This is one subtree, this is another subtree, and this is one more subtree. So hence we say the degree of the root node A is 3, and if I take the degree of the node C, it is 1. Okay, node C, it is 1 because you got to take into account only the subtree of a particular node. Okay, so for this now, so there is only one subtree, there is only one child which is present. Hence we say the subtree for the node C is G, and since this is the only subtree for the node C, so the node degree of C is also 1. Okay, and the thing that is written here, to the left side of a node is the node degree. Okay, so node degree for the node A is 3. How do we say it is 3? Because it has 3 subtrees. And node degree for B is 2 again because it has got 2 subtrees. And the number which is written towards the right of the node is the level. Okay, so the level of the tree. So this node B is present at the level 2 of this tree. And similarly for C, it is the node degree 1, and it is at the level 2. And D, node degree is 3 because it has got 3 subtrees. Okay, and similarly for E, so since there are 2 subtrees, so this is 2, the left side number is 2, and the right side number is 3 because it is at the level 3. Now if I take K, okay, so degree is 0 because it doesn't have any left subtree or the right subtree. Hence the node degree for the node K, leaf node K, is 0, and it is at the level 4. Okay, so something similarly it's written for all other nodes. So you understood this. Okay, and the node degree node with the degree 0 is a leaf node or a terminal node. So obviously, so only the leaf nodes will have the degree as 0. So you can call them as leaf nodes, or else you can also call them as terminal nodes. Okay, a node that has subtrees is the parent of the roots of the subtrees. Okay, so this also you know, and roots of these subtrees are the children of the node. The children of the same parent are called the siblings. So all these things you know. So now say this A, B, C, D, so all the siblings because they are all the child of this root node A. Okay, the ancestors of a node are all the nodes along the path from the root to the node. Next, now representation of trees. Okay, linked representation. So I have this, the root comes first, followed by a list of subtrees. Okay, so I'm writing the data for the root node here, and these are all the links for the subtree. Say for example, so I want to implement this itself, so this tree itself. What I'll do, I'll take a node. Okay, I'll take a node and I'll write the information field to the data field of the node, and how many link fields should be there. Since this node has got 3 subtrees, so I got to have 3 link fields in this node. And similarly, when I'm taking the node of node B, it should have 1 field to hold the data or the information, and 2 more additional fields in order to hold the address of the left subtree and its right subtree. Now if I take the node C, so 1 field for holding the data and one more link field for holding the address of this subtree, its subtree. OP people are following?
Yes, sir.
Okay. Now, see, same thing I've represented here, something like this. See, this tree in the form of a linked representation, it is something like this. Okay. A is the root node. Okay. And then, so just observe here. A is the root node, and it is written here. I've written here. And now, what are its subtrees? Subtrees of A: B, C, and D. Look here. So B is a subtree, and C is another subtree. Okay, and D is one more subtree. Okay, and B again. If you take B as two more subtrees, E and F. E, and this E again has two subtrees, K and L. K and L. Okay, and subtree F, that's all. That itself is the leaf node. Okay, and then comma. Then C as one child node, that is G, and D as which one? H, I, and J as the subtrees, and H in turn as M as the subtree. This is how you can go for doing the linked representation of the trees. Okay, and so, and how do you represent a node? Something like this. Say this node A, if I want to represent, I need one data field, and in addition to this data field, how many link fields are required for me? So one link field for holding the address of the subtree B, and one more link field for holding the address of the subtree C, and one more link field for holding the address of the subtree D. Okay, and so when I take the node B, again it should have one subfield for holding, so one link field for holding the address of the node E, and one more link field for holding the address of the node F, or the subtree F. And then E in turn should have two more link fields to hold the address of the node K and address of node L. It goes something like this. Is that clear?
Yes, sir.
Okay. Now, left child and right sibling. So this is how we represent a node now. Okay. Data left right. So this A is now is the root node. Okay, which has only one subtree now, that is B. Now if I take B as two subtrees, so one is this, and another one is this entire thing. Okay, and then C, there is only one. Okay, this is one more. So this representation what I told you. Okay, so this linked representation, something like this. So it looks like this. Okay, so A, so it's exactly same as this, you can just relate it. A, okay, to B. Okay, see, something like this. In this root node you store the address of left child, and using this left child you can reach all these siblings. Okay, see, C and D are the siblings to B. Okay, now in A, what I'm doing, instead of holding or creating the links for every subtree, what I'm doing, I'm just storing the link for only the left child. Okay, now from the left child I provide a provision for reaching the siblings C and D. Same thing from A, so I cannot directly go to C and D, but from A I can come to B. Now once I am here in B, so I can go to the siblings C and D. Okay. Similarly, now from B, see B, if you look into B, so B also has two child nodes. Now in B, I provide link only to the left child, that is E, and from E, I'll provide a link to the sibling F. Same thing. So from B, I have a link to the left child, and once I reach the left child, I can go to the sibling F. And similarly for E also has two child nodes, K and L. From E, what I am doing, I am reaching K, okay, the left child of E, and from K I can go to L. So you can have this kind of representation also. Okay. OP people are following what I am saying?
Yes, sir.
Yeah. Okay. Now, so left child and right child tree representation of the tree. Okay. Now here left child and right child. Okay. Observe here. So this first node is holding the address of its left child, and then the left child, it was holding the address of the right sibling, and this sibling here, holding the address of the right sibling, one more sibling. Okay, and this is one more way of representing by using the concept of left child and right child. So this is left child and right sibling. So this is left child and right child. Okay. So here, let me copy that diagram here. It will be easy for you to understand. So left child and right child tree representation. Okay. So the left child for this root node A is B. Okay, and then the left child for this B is E. Okay, you can reach here, and the left child for E is K. You can reach this. Next, right child. Okay, now the right child, for I want to reach the C and D. What I'll do, I'll come to B, and B, the left child of A, will hold the address to its right child. Now what is it? C. Okay. Now when I come to C, okay, so it has one left subtree, and C is holding its address, and similarly, so there is one more siblings, so the C also holds the address of its sibling. Okay, so this is another way of representing the tree. Okay, so left child and right child. Okay, any doubts till here?
Sir, B will hold two addresses, no? Like
yeah, B is
E
hold.
E.
Yeah, E and C. Okay. See, what B is holding is, it is holding the address of its left subtree, and B is also holding the address of its right sibling.
Yes, sir. Yes.
So same as this. Okay. Now what? See, so C was holding same as this. Same as this. Understood?
Yes, sir.
Okay. So next is binary trees. So a binary tree is a finite set of nodes that is either empty or consists of root and two disjoint binary trees called the left subtree and the right subtree. Okay. A tree can be formed into binary tree by left child and right sibling representation. So the left subtree and the right subtrees are distinguished. I'll just show you with the example now. Okay, so instead of going with all these things, I want to take a simple example and show you. Let me insert an empty slide here. Okay, sorry. Let me take say for example 1, 2, 3, 4, 5, 6. Instead of taking it in order, let me take some unordered number. 5, say 2, say 6, say 1, say 7, sorry 8, okay, 0, 7, 1, 2, 3 is missing. Let me take 3, 1, 2, 3, 4 is missing, 4, 1, 2, 3, 4, 5, 6, 7, 8, 0. Okay. Now I want to represent this using the binary trees. Now what I'll do is I'll start with this. I'll take the first number and I'll make it as the root node. Okay. Let me show you. Insert shapes. Add text. So I'll make it as 5. The first node, the very first node, I'll make it as a root node. Next, what I'll do, let me copy this. Okay. So the next number is 2. Now where I have to insert this? So do I need to make this as the left subtree for 5 or the right subtree? Okay. So you just compare. So if 2 is lesser than 5, so it should be made as what? The left subtree. Okay. If it is, see, the very first number, you make it as the root node. When you are reading the next number, just compare that number with this root node, info field of the root node. What is the info field of the root node now? 5. Now 2 is less than 5. Okay. Now whenever it is lesser, you should be inserting it to the left subtree. Okay. So 2 I'll add here. Okay. And then done. Next I take 6. Okay. Where to insert 6? I'll just start with the root node. Okay. I compare it with 5. Now 6 is greater than 5. If it is greater, now where it should go? It should go to the right subtree. Six here, and then correct now? Are you following?
Yes, sir.
Yes, sir.
Next number which is scanning is 1. Now again you start from the root node. You compare this 1 with 5. 1 is less than 5. Where you have to travel? You go to travel along the left subtree. Okay. If it is lesser, you have to travel along the left subtree and then insert at the appropriate position. Next, I take 1, I compare it with the root node. So 1 is less than 5. I'll travel this. I am here now. And again, I'll compare this 1 with 2. 1 is less than 2. Now where it should go now? So 1 should go as the left subtree for the node 2. Okay. One comes here. Is it clear?
Yes, sir.
Next 8. Okay, take 8. Compare it with 5. Okay, 8 is bigger than 5. Now which tree you will travel? Left subtree or the right subtree? You have to travel along the right subtree. So come to this node. Okay, compare this 8 with 6 again. 8 is bigger than 6. Now this 8 should be inserted as the right subtree for node 8. Sorry, node 6. It comes here. Next 0. Okay, so compare with 5. So 0 is less than 5, so you got to travel along the left subtree. So you'll reach 2. Compare 0 with 2. Again 0 is less than 2, travel along this path. Now you reached 1, and 0 is less than 1. It should be inserted as the left subtree for 1. We have 0 inserted as the left subtree. Next. So next input symbol is 7. I will start from here. So 7 is greater than 5. So I will travel here. And 7 is still greater than 6. So I will travel this path. Now I will compare 7 with 8. 7 is less than 8. Now the 7 should be inserted as what? The left subtree for 8. So 7 is inserted as left subtree to 8. Okay, next 3 I take. So compare that with 5. So 3 is less than 5. I come to 2. Now I'll compare 3 with 2. So 3 is greater than 2. Now 3 should be inserted as the right subtree for 2. Three, and it is the right subtree to it. Next 4 I take. I'll compare with 5. 4 is less than 5. Again I got to travel along the left subtree. I compare 4 with 2. 4 is greater than 2. Now I have to travel along the right subtree and compare 4 with 3. It is bigger than 4. Sorry, 4 is greater than 3. So now 4 should be inserted as the left subtree. So let me okay. Now one more node. Which is inserted as the right subtree. Great. Hope you understood this. Sorry, this is 4. Is it clear?
Yes, sir.
Okay. So now how many levels are there again? This is level 1, level 2, level 3, and these nodes are at level 4. Okay. Level 1, this is level 1 if I write. This is level 1. This is level 2. This is level 3. So all these nodes 1, 3 and 8 are in level 3. 0, 4 and 7 are in level 4. Okay. So if you want, I think I cannot write here. I have to insert a text box and then write. L1. This is L2. 3 L4. So this is how you can go for constructing the binary tree. So I hope you people understood how to build the binary tree. Yes? Am I audible?
Yes, sir.
Okay. Now take one more example and try to do it. Okay. Try to construct the binary tree for this. I'll give one example. So 10, 9, 7, 0, 1, 2, okay, 1, 15, 16, okay, 18. Yeah, write for this. Write and share it in the chat box. Write and share it in the chat box. So meantime I'll finish taking the attendance. Three 50, 43, 135, absent, 156, 10, 16, absent, 39, 116, 134, 135, 136, 137, 138, 140, 141, absent, 142, 143, 144, 145, 146, 147, okay, 148, 149, 150, 151, 152, 153, 155. One 56, 157, 158, 159, 160, 162, 160, 159, 160, 162 absent, 163 also, 164, 165, 166, 167, 168, 169 is absent, 170 absent, 171, 172, 174, 175, 176, 77, 178, 179, 180, 181, 182, 183, 184, 185, 86, 188, 189, 190, 191, 192, 193. Okay. So have we finished? So I have got one response. It's still loading. Okay, I'll check it later. So those who have finished, just post it in the Teams. I'll verify it. Okay. So 10, okay, 9, 15, and then 7, 0, 2, 2. Okay. Okay. Yeah, it's correct. Okay, so we'll end the meeting here. Thank you. We'll meet again tomorrow.